All right. You guys all have to watch me type my password. Now, Rob, you're messing me up. Stop. How did you know? Are you spying on me?
Yes.
There we go. All right. Perfect. Well, I should go over here. I see a few less faces today than I did yesterday at the conference. I'm not sure if after lunch or after the after party is the best speaking slot. So anyway, my name is David Bianco. I'm here to talk about some threat hunting kind of content. We got a little bit of that yesterday. I was really happy to see that. I was a little bit worried on the beginning of the conference. Everyone was, these are all these talks about things I've attacked and things I've hacked into. I don't do that sort of stuff, so I was a little bit worried about that, but we got some good threat hunting content in there, so I'm really happy. I also learned a lot yesterday, not only about how to attack things, but I learned that there are apparently 3 things that you need to have in every presentation. I learned the obligatory 3 things from Rob Fuller. So these are my Robligatory slides. I found if you misinterpret Sun Tzu, which everyone probably does, right? You can find some really interesting things in here. So I've willfully misinterpreted a few. Here's the blue team edition of The Art of War. You can be sure of succeeding in your attacks if you only attack places which are undefended, Rob. But I'm doing one up on him. I have 2. So the red team edition of The Art of War has probably what the red team thinks of the blue team. You can ensure the safety of your defense if you only hold positions which cannot be attacked. Oh, I'm missing a slide here. Nope. So this is a presentation on something that some of you might not have thought that we would really be talking about at a professional security conference, and that is data analysis. Sorry, it's all about numbers and data rather than that much actual security content, but this is really important for folks who are trying to find the bad guys. We had a talk yesterday about cyber security analytics. So this is a piece of that. I run a website called threathunting.net. And threathunting.net is just it's a simple project that goes, and I look all over the internet and all the different places I can find to see people who have published successful recipes for threat hunting, how to find bad guys in piles of whatever kind of data. And it's indexed by, I'm interested in finding lateral movement, or I'm interested in finding data exfiltration, or it's indexed by, I have HTTP proxy logs, what can I find in them, and things like that. But one day not too long ago, I was looking through all of the recipes that I've cataloged in there just to try to get an idea of what some of the data analytic techniques are being used out in the field. And I noticed 2 things. And one I already kind of knew was that much of the threat hunting involved finding some kind of anomaly or outlier in some data set. Usually it's a behavioral anomaly, but a lot of these are translated into numbers or something so that you can use mathematical outlier techniques in theory. But what I really found was that in the majority of cases, the only outlier technique or the only anomaly detection technique that was being used, there was only one in all of the different recipes. So I thought, that is terrible. not that it's terrible that there's one good technique out there, but it's terrible that we're trying to fit this one technique into all the different ways that we would want to detect anomalies. So I decided that I should write a presentation just to give a little bit of, in some cases, a reminder, and in some cases, some new techniques that people who are doing data analysis for threat hunting can use to find bad guys in their data. So that is the primary purpose. I think the secondary purpose here at f-kʒn actually would be also for the folks that are not really doing the data analysis to find the bad guys, but are actually the pretend bad guys. It may give you a little bit of insight on some of the ways and methods that folks on the blue side might be using to detect your activities. Come on, go back. All right, I'm also another one up on Rob because not only do I have a cat picture and a meme, but they're the same. I've combined them. The first, just start with a very brief definition of what an outlier is and why we care, right? So most of the time, and I think probably everyone in this room would agree with me, I hope, that when you are an attacker in a network, whether you're a legitimate red team member, a pen tester, or even an actual threat actor, even though you try really hard to mimic the behavior of a legitimate user in an environment, at some point you have to deviate from a legitimate user's behavior in order to accomplish your goals. Now, the art of threat hunting, the way that I do it anyway, is to find those deviations, interpret them to see if we think that they're a malicious deviation or not. And every time that you deviate from a normal user's behavior, that's an opportunity for us for detection. So remember I said that every threat hunt that I cataloged pretty much had one technique. Well, this is the one technique for outliers that everyone knows. Its real name is called least frequency of occurrence analysis, although you will sometimes often hear it referred to as stack counting or stacking, and there might be some other terms as well. But it's basically very simple. You have a column of data, and you're looking at that data. You count up all the unique terms in that data and see how many times each one occurs, and then you sort them by that count. Usually, you're looking for the least common things, so the low end. So you do like an inverse sort. Now here's an example that I got from a publicly available insider threat data set that just says, I wanted to find the least commonly accessed files in this data set. Now, the implicit assumption in this, and pretty much in all least frequency of occurrence analysis, is that anything that's infrequent is automatically considered maybe not bad, but at least suspicious. In some cases, that's probably true. There we go. So just to give you an idea, if you've never done this, or maybe it has been a while, one of the reasons I think this is so popular is that it is super easy to perform. And most of the data analysis tools that you would have actually can do this built in. You can see I have 3 different mechanisms here on the slide. For SQL, just a regular relational database actually does this pretty well. If you're using Splunk or something like that, you know, you have the stats module that you can invoke that basically does this exact thing. And a lot of times the things that I do, I actually write custom code in Python, so you'll see a lot of Python, well, you'll see a little bit of Python in this presentation, and you can see using a data analysis module called pandas, which is a very common data analysis in the scientific computing realm. It basically does this in all three of these in about one line. So it's conceptually very easy to understand, and it's well supported in most of the tools. So I said that maybe this is a bad idea to have it only one, but there are some strong use cases for this. This is an example of something that would be appropriate if you are working with, first of all, enumerated data, that is not numeric data that would have potentially infinite number of possible values, but you're working with enumerated data, usually strings, but sometimes things like TCP port numbers or something, which are not really integers, even though they look like it. So they should be enumerated or maybe categorical values. Also, you have to really think hard before you try to use this. If I find something that's rare, do I really think that that's suspicious? You really have to kind of evaluate the context in which you're using this. But on the other hand, it's very easy to implement. So that's probably why it's so popular. I will say it has a number of weaknesses, though. Some of the other techniques we'll talk about address these weaknesses. But first of all, if you're working with numeric data, you probably, this would be a bad use for numeric data. Also, if you have more than one field per data point, so if you think of like maybe a database with multiple rows or multiple fields, you can actually do this with 2, 3, 4 fields, but as you get up to some more complex things, the more different fields that you have for each of your data points, the harder it is to do this kind of LFO or stat counting analysis. I also find it's kind of hard to adapt to automated alerting because you're just looking at a sorted list, and you have to, if you're going to make it an automated alert at some point, and by the way, I think that's the goal of most threat hunting, is to try to figure out the thresholds and the signatures for automated alerting. I'm not anti-signature person, but this is a good way usually to get signatures through threat hunting, figuring out what those values should be for automated alerting. But it's hard to do in this case because you just have a sorted list, and it doesn't necessarily follow that a value of anything 5 or below is always suspicious. It's just a sorted list. You see this turned into a lot of dashboards because as a human, we can have that list prepared for us, and then we can look at the dashboard and kind of make some judgments. But when you're thinking about automated alerting in a SIM or something like that, it's hard to do with this. Also, even as a human in a dashboard, working with the dashboard, we tend to have a really long tail of results from LFO analysis. You might see in a big organization, if you actually did that example I had about the files that were least frequently accessed, you might have 1,000 files every day that only had 1 or 2 accesses that you'd have to check. Now, on the bottom here, you'll see I have kind of a problem statement. This is more or less like a model of what I think a good example of a use case for stat counting or LFO would be. So I've never seen this service before in any of my 100,000 systems in my environment, so it's probably kind of suspicious. The closer that you are to that kind of statement, the more likely it is that this is an appropriate analysis technique for you. But if the farther you get from that statement, the more likely it is that you should be looking for something else. Well, what else? The next 2 techniques I'm going to show you are a little bit of simple visualization. The human brain is really surprisingly good at processing large amounts of data if you can only present it in the correct way. In most cases, in many cases anyway, the correct way will be to make use of some of our built-in pattern recognition that we've developed over thousands of years. If you actually look at that, that's just a piece of toast, right? But your brain probably can not help but see what? Elvis on toast. And if you didn't see it before, you probably can't unsee it now. Your brain is very fine-tuned to get information visually and process it efficiently. So let's make use of that in our threat hunting. So the first technique I want to talk, The first technique I want to talk about, you probably all learned in like high school science or math class. It's just a general scatter plot. But it's amazing that I never once saw a scatter plot show up on threathunting.net, except for I contributed one after I realized that this, this was not on there. So it is on there. There is one there now. But this is the result of an analysis I did on some test lab simulation data to try to find hosts that were performing data exfiltration by using a metric called the producer-consumer ratio, which I have a blog post on this. You can look at my blog online and read the whole thing if you're interested. The basic idea, though, is most computers on the network act the same in terms of the number of bytes they receive from the internet and the number of bytes they send to the internet. They're roughly the same over any given time window. So basically what I did is I had a method to compute the producer-consumer ratio for 1 week of activity for each computer. Each dot on there is one computer in the test lab. And I computed it for the subsequent week. So I computed it for 2 weeks. And the y-axis is the previous week, and the x-axis is the previous week, and the y-axis is the current week, and I'm looking for data exfiltration in the current week. So if the host doesn't change, all the dots line up on this line. And you can see we do have a lot of dots that line up pretty close to that line. Now, if the host does change in a way that is positive, the ratio goes positive if you're sending more data to the internet. So we have things that fall above the line. For some reason, we also have a few hosts that downloaded a whole lot more of information from the internet than they did previously, so they have negative outliers as well. In this case, since we're looking for data exfiltration, we're primarily concerned with the positive outliers. So, and you can see actually our most outlier-y host did really turn out to be our data exfiltration host. So before, when I talked about LFO, I showed you 3 different ways you could do it in different tools. Most of the tools that I'm aware of today don't really have this like as a built-in thing that you can just call and do it. But I typically do a lot of my things in Python anyway, so I thought I would just show, and this is not a quiz, you're not going to have to reproduce this in running code later, but just wanted to give you an idea of kind of what the level of effort is to produce a scatter plot. It's not really difficult. I'm using a library called Plotly on mine, but it even gets simpler if you use like a matplotlib or something like that. But really we only have, here's all of our data, the x points and the y points, and we call iplot, and it does the thing. There's actually no real reason that as a threat hunter you can't produce a scatter plot in just a few seconds. If you really need the scatter plot, it's pretty easy to do. So scatterplots use cases. Scatterplots are really good when you have numeric data that you want to compare on 2 axes. So you basically have 2 numbers. The malicious data would be assumed to violate some clear correlation. So on mine, the correlation was they should go on a straight line. If there's no change, that may not always be the case. Sometimes you'll see things like, oh, I have a cluster of dots over here, and then I have a few dots elsewhere that are out of the cluster. Those are the ones violating some correlation. Just depending on what you're looking for, the pattern that you see might be visually different, but you'll be able to hopefully see the outliers kind of visually very quickly. And sometimes you just need to test whether the correlation even exists at all. Like you expect that there might be a correlation, Or possibly even you're not even sure if there's a correlation. You just have a bunch of data points to try out. And you want to see if there is any correlation. You can throw them in a scatterplot. Scatterplots are great when working with numeric data, but they're kind of weak for some things too. So the things that you would use stat counting for, numerical or enumerated data, really is difficult to do in a scatterplot. And it's possible you can convert them to numeric values and plot them, but it's not really clear that that's usually a useful thing to do. So if you're working with non-numeric data, you're probably not doing scatterplots. Sometimes you'll find that the values have weak or no correlation. You might throw it up in a scatterplot and find that they're just randomly distributed around. That's okay, you found something that you didn't know before, but may not be too helpful to you all the time. And sometimes if you need to compare more than 2 or 3 numbers. So you can kind of do a 3-dimensional scatterplot if you are a little bit creative. So you can compare 3 numbers at a time. But if you get past that, you're really in the 4th dimensional kind of Doctor Who realm. A little bit hard to visualize that unless you are a Time Lord. I got one laugh, that was good. So again, here's a kind of like an ideal problem statement for one example of why you would use a scatterplot. So most users don't change upload habits often, so benign activity should fall close to the no change line, right? This one's a little bit more open-ended than the stat counting version, but in general, the closer you are to a statement kind of like this, the more likely it is that scatterplots are going to be good for you. All right, that was the end of the science class review of scatterplots. Let's talk about something that you may or may not have heard of before. Probably if you have a statistics background, you've seen box and whisker plots, but if you've never taken a statistics class, these might be kind of new to you. A box and whisker plot is basically just a way of showing with one column of numbers kind of the shape of the distribution. Do they all cluster around certain values? What are the maximum and minimums and things like that? And so you can see here I took some from our production environment. So one of my hunting hypotheses was that possibly if I looked at all of the instances of PowerShell running in my environment and I just compared the length of the command line, that I might be able to determine some which were more likely to be like a red team or a threat actor pushing a PowerShell script through my environment rather than somebody just using PowerShell to initiate commands from the command line interactively. I'll tell you this actually didn't turn out too well because lots of automated processes have giant PowerShell scripts in the command line. But as an example of how to do a box and whisker plot, it actually works really well because you can see here, I'm going to show you a few features of the whiskers and the box and whisker plot. There's this thing in statistics called the 5-number summary. The 5-number summary of a set of data it's intended to give you this shape of the data, and the box and whisker plots is a visualization of the 5 numbers. So you have, first of all, the minimum values on the whisker and the maximum value on the whisker. Ignore the fact that it's not actually the maximum value for a moment. So consider the minimum and maximums. And then you have the 25 percentile, the lower end of the box, which means everything under here, 25% of the values are under here, basically. And this is the 50th percentile. So this says basically half of the values are under here, and the 75%. So 3/4 of the values are under here. That's really all there is to reading a basic box and whisker plot. The interesting thing, and the reason I like this so much, first of all, it's super easy also to produce one, but it's maybe the only visualization that I've seen so far that explicitly calls out the outliers. This. Anything above the top whisker is technically considered an outlier. So you can visually see that if you were to just ignore the box plot here and look at the kind of scatter plot that I did, it's not necessarily clear where the correct outlier range might be. You might set it here, you might set it here, you might be tempted to set it right here at like 300, but actually the box plot here indicates that the correct answer is just a shade under 400. And so we have this thing that's like 500 characters long. What was that? It's like it immediately pointed out which thing I should probably be looking at. There's a different version of the box plot here that adds the standard deviation. Actually, it adds the mean here in the middle, the dotted line, and then the diamond is the standard deviation. So it can, as an alternative, some people use like here's a quick bonus outlier method. As an alternative, when you're computing outliers, not visualizing them, but you're just computing them, a lot of times you'll see people say they'll pick either 2 or 3 standard deviations and say if it's 2 or 3 standard deviations above the mean, then it's an outlier. And if you actually look at this, this is the mean, and this is 1 standard deviation, 2 standard deviations. It's pretty close to the top of the whisker. Again, this is really not complicated to produce. Most of this is actually turns out to be formatting to make it look pretty for the report that I was creating. And here's really all of this is just the list of data points. I'm just creating a box plot, and again, I'm calling iplot. So in fact, even though this is like 7 lines of code really or something like that, you really could do it in like 2. So box plots, first of all, are really strong when you have, first of all, univariate data, which means you're only having 1 variable. You can't really do a box whisker plot on anything where you have multiple variables that are correlated. So you're only looking at 1 column of data, and it's numeric data. Again, it has to be numeric data. It's really nice because you can just kind of visually see the shape of the data distribution. Do all the points cluster to the bottom? Are they uniformly distributed? Do they cluster to the top? Whatever. And the outliers are shown explicitly anything outside the whiskers. Sometimes the whiskers, you'll be interested in the lower outliers, so things below the bottom whisker, and sometimes you'll be interested in things above the top whisker, the high outliers. But they're visually shown, so it's very easy to identify them and zero in on them. And the outlier thresholds usually are really easy to convert to signatures. So in my mind, when I was doing this hunt, I thought, well, if I do find the outlier, what I will do is maybe find that value in my data set and then take that value and do a larger search and say, show me all the PowerShell executions for the last 6 months that have command line length greater than 400, right? Again, that didn't really turn out to be a useful hypothesis. My hypothesis was wrong, but that's how I would have turned that into an automated signature. And again, here's the kind of ideal use case. I have no idea what's normal for this column of numbers, and I just want to find out. And I'm not even sure if there are any outliers in it. But if you have that box plot, and in about 3 seconds, you'll know the answer. Ooh. There we go. Wow. Okay. So box plots are really cool. I like them more than I really should. But I promised you 4. How am I doing on time, by the way? Good? I promised you 4 techniques. So for the 4th technique, I'm going to do something that's not visualization. It's actually really good when you can't visualize something, especially because it has too many dimensions. We're in the Doctor Who area that I was talking about earlier. And this is a technique that I would be a little bit surprised if very many people have heard of. It's called isolation forests. Isolation forest is actually a kind of new unsupervised machine learning algorithm. And the idea here is you have some data that has potentially very many, maybe hundreds or even thousands of variables for each data point. And you want to find which ones are more unique than the rest of them. So what we're going to basically do is a shortcut version of something that you might have heard of called clustering, where we take all the data points and find the ones which are really close to each other, and then anything that's not really close to one of the clusters is considered an outlier. But clustering, the traditional way, kind of has some drawbacks. In the sense that it's really hard to do correctly, and sometimes you have to know a lot about your data in order to understand, for example, how many clusters there are likely to be and things like that. But this technique doesn't really require that. It's also super efficient. So here's the idea. This is, again, a scatter plot. We've done this clustering on here is a two-dimensional clustering, so you could have just used a scatter plot for really. But this kind of gives you an idea of what's going on. Each dot here is one data point, and because we're only working with 2 dimensions, that means we have 2 variables or 2 fields for each data point. What you do when you do isolation forest is kind of simple, but maybe is a little bit confusing at first, so I'll try to go through it. What you do is you take a random variable and a random value, and you take a data point and you split the field of all your data at that data point and that random value and that random variable. So here's what we've done. I shouldn't say we, this is not my diagram, but here's what they've done, is they've taken the data point that falls on this line. I'm not sure if it's this one or this one, but and they took at random, they picked one of the 2 variables and they split it. So you have everything above it and everything below it. But then they continue splitting it, and they say on this side we're going to take another random one. We'll take one of these guys here and split everything below it, everything above it. And they keep splitting it, and every time they do it, they do a random direction and a random value. So the next time they split here, maybe, and they split everything to the side, to the right, and they keep doing that until you come to an area that has only 1 point in it. Are we with me so far? Right? And what you do, and then, is you have counted the number of splits that you have to do to get that 1 point, and you assign that number to that 1 point. Maybe that point has 4, or maybe it has 26. And you do that until every point on the graph has its own number of splits. And because each one of those was a result of a random series of decisions, right? You save all that data, and then you start the process over again. And you make a different set of random decisions until every point has its own number. And you do that over again, and you do that several times. And the reason is just to kind of correct for the randomness of it. The more random versions of the thing that you have, the more likely they are to agree when you come to the next step, which is you just take the average for each data point. The data point had 5 splits, 7 splits, 6 splits. You average all those, and you're somewhere around 6, right? So that's the data point. That's the final value for that data point is 6. Each one of those sets of splits is a tree, and when you put all those trees together, you get a forest. Therefore, you're finding the forest of how long it takes to isolate each point, the isolation forest. And the average depth that you have to go to before you split any given point tells you how likely it is that this is something close to everything else, because these guys in here are more likely to need a lot of splits. So you can see here, they took all these different splits to find that one data point. And I don't even know how many that is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, something, if I'm counting right. So this is pretty clear visually, right, that this is close to most of the other points. But here's this point over here, and it took 1, 2, 3, 4, 5. It took like half as many splits. So in an isolation forest, the number of splits, the larger the number, the more likely you are to be an inlier. The smaller numbers, the more likely you are to be an outlier. So you can actually just feed it a bunch of data in multiple dimensions, and it will do this thing. And these things are, the isolation forest is actually well supported in Python in this library called scikit-learn. Unlike the other ones, it takes a little bit more code than I thought would be useful to put on a slide. But I have a GitHub repository that my friend Chris McCovett and I put out a kind of sample code for using isolation forests and a couple of other machine learning techniques to go through, in our case, bro HTTP log files to find the most unusual looking log values. So it was a kind of experiment to see whether we could actually use a technique like we did random forests and isolation forests to see if we could use those techniques to find the individual log items that we needed to look at and not have to look at, 100 million log entries a day. The short answer is that works. It's on GitHub, and you can give it a try. And if you want to see the still pretty simple source code that it requires to create isolation forests, it's up there, and I encourage you to take a look. So, isolation forests. Why would you want to use them? Well, there's a few things. First, if you have numeric data and you have a lot of different variables, you can't easily visualize all those at the same time. Most visualization techniques would require you to take a couple of those variables by themselves and visualize them, and then take another set and visualize those, etc. Visualization, we're not able to think in 300 dimensions, but isolation forests can do that, no problem. It needs to be numeric data though, but you will see, for example, if you go to our GitHub for Clearcut, that we've taken bro HTTP log files, which are mostly not numeric, and we convert the strings and the enumerated values into numbers so that we can apply this technique. So this works best on numeric data, but if you don't have numeric data, you may be able to convert to numeric in a way that makes it useful. It's also pretty performant even on a laptop. You can use isolation forests to process a pretty large amount of data pretty quickly. And it has a lot less machine requirements than some of the other more complicated clustering algorithms. But I think the most important thing about this is that you get to go to your boss and say, "We applied machine learning to that problem, sir." Everybody likes to have machine learning. So some of the weaknesses of it, that conversion of non-numeric data into numeric data is maybe not technically that challenging, but there's probably a lot of pieces to it, and it's kind of tedious at some level. So, and it's also difficult. Again, it's difficult to visualize. So it's easy to tell somebody, well, our analysis said this is an outlier, and if they want to know why, it's really hard to be able to tell them just based on isolation forests why it was an outlier. You won't get the kind of detailed explainability, but that's okay. And again, so here's our sample problem statement. Which of these log entries are most unlike the others, right? So closest that you are to this, the more likely it is maybe that you could benefit from trying isolation forests. So the main takeaway that I want you to get from all this is David is boring. No, that's not it. It's math is hard. No, that's not it. The main technique is the main takeaway is that please don't just automatically go to stat counting and least frequency of occurrence when you have to find outliers. There are other things that we as a threat hunting community should be able to use. And by no means are these the only ones, but these are just like the four that I think are kind of most useful and most interesting in combination. So you could certainly we've talked about cases where stat counting and least frequency of occurrence is totally appropriate, but we've also seen scatter plots and box plots for visualization, and then we've even learned to impress our bosses with our machine learning abilities. So I would say don't be afraid to try some of these techniques, and the next time you have a big pile of data in front of you, don't be afraid to try a different technique. There's nothing magic about just these four techniques. There's plenty of other outlier techniques out there that are really useful, and I hope if you experiment with some of them that you will end up writing some of your stuff up and submitting it to the threathunting.net. So at this case, this point, I have questions.